Okay. Good afternoon, students. Welcome to the today's lab. Okay. This is lab number 3. This is lab number 3. And the lab number 1, introduction to the FPGA and the HDL programming, and what are the concepts are there in FPGA that we have discussed. And the lab number 1, recap. Lab 1 talked about exclusively FPGA and Vivado tool demonstration, tool demo that we have talked about. And lab number 2, we talked about introduction to HDL programming and some combinational circuits we have described. Okay, some combinational or circuits design that we have seen. Today we are at lab number 3. We focus mainly on structural modeling here. We focus mainly on structural modeling. Okay, we talk about exclusively structural modeling. It is in the combinational part. Okay, we talk about in the combinational part. My voice is audible, students? Hello?
Yes, sir.
Yeah, fine. Thank you. Okay. Now, the today's objective is, or aim of the today's programs are the 4-bit adder. Okay. Next, we would like to see 8x1 multiplexer. It is using full adders, 1-bit full adder. It is using 2x1 mux. Okay, and we'd like to discuss about 3x8 decoder using 2x4 decoder. Okay, if possible, 4-bit comparator. Comparator using 1-bit comparator. So these are the topics that the today's class. I will discuss one or two, and you have to do the remaining things. Okay. Is it clear to all of you what is our objective of the today's lab? So these programs you have to run in your Xilinx Vivado. Okay. So as I mentioned that in the part number 4, I think so, we will implement all these programs in an FPGA. Okay. So what are the necessary things are there? Those things also will be discussed there. Okay. So this is what the today's lab objectives. Okay. So let me explain first of all 4-bit adder or maybe multiplexer. Okay, the adder already we have seen in the previous. So what is the structure, how it look like, all these things we have seen previously. Okay, better I'll go for the 4-bit and 8x1 multiplexer. Okay, so because already we discussed about the adder in the previous class, so we'd like to do that one. Okay. So modeling of 4-bit adder. Okay, so which means that it doesn't mean that we are adding the 4 bits. It's not the meaning of the sentence of 4 bits. It says that the adder has the adder is essentially two operands. One is A, for example. The second one is B, for example. An adder has got two operands. One is called A. The second one is called B. And each and every operand is of size 4-bit. That's what the meaning of the 4-bit adder. Obviously, it will generate the sum signal that is called S. It is also generate the 4-bit output. Okay. And it is usual practice, and it's very important when we are realizing the bigger circuits. Okay, so therefore it's necessary to provide extra signal that is called the CN signal. This is useful when we are realizing a bigger circuits. Okay, because by using the 4-bit adder we want to do something else. Okay, so then it's very useful. Okay, therefore it will generate the output called C out. Okay, so see the CN is one single bit size, that is also a single bit size. The question is that what is the inside of this particular adder? Okay. Okay. What is the question of this one? Okay. So first of all, the objective is that we would like to write the program using structural modeling, right? That means inside structure is important for us. Okay. So what is the inside structure of the 4-bit full adder? So the constraint is we have to use 1-bit full adder, 1-bit full adder, 1-bit full adder. Okay, 1-bit full adder one and the same. Okay, usual ga 1-bit adder antamu, ledante 1-bit full adder also. Okay, so that means I have to consider 4 1-bit full adders, right? I have to consider 4 1-bit full adders. Okay, such type of 4 things are required. Two, 3, and 4. Okay. So what is the inputs and output of this one? Usually we would like to write a MSB bit position LSB here. This is called FA0, the name of this adder. LSB stands for the next one. This is also the last one. This is the MSB, right? Agreed? Now, what I can do here is that I would like to write CAN here. So I would like to write CN at this point. I would like to write CN at this point. Okay, fine. Now what we can see here, we have a CN signal here. Okay, yeah. So it requires another input signal that is called A. Since I'm writing the vector notation, it is usual practice we need to write in this one. A of 0 and B of 0. Okay. ఇది A of 1, B of 1. Get this design, you know very well from the basics of EDs. Sorry. Yeah. Now you can see here is A1, and this is called B of 2. This is called A of 3. This is called B of 3. Right? So since I'm writing the vector notation, it is what we have to write. Of course, this design you know very well in the previous classes. Okay, so the output of this one carry information is connected here. This will be now the C of 0, let me call, okay, because this I want to write it in external vector notation only. The output of this one is required to calculate the FA2. This is called C of 1. The output is connected here, C of 2. And I'm taking the outside C out something like this. And of course it is produces. The outputs are called S of 0, S of 1, and this is S of 2, and this is called S of 3. Okay, so therefore the bit by bit we are able to, this is the bit we have to use to calculate, for example, something like this. Let us take 1010. Okay, 1101. So what we are doing here, so assume that there is a carry input signal is there. So for this one, we have to add these three. First of all, it will produce the sum signal S of 0. It will produce the sum signal called S of 0, and it will produce C of 0 as carry information. We have to all this add these things, and it will produce S1. It will produce C of 1. So add all these things S of 2, and it will produce C of 2, and add all these things, we'll get S of 3, and it will produce C out signal. So the same logic we are implemented using this structure. Okay, so this is how we need to write. Better I need to take a, this is the entire block. This is the entire block. So this is what inside of the, this is what inside of your black box. Agreed? Now we know the structure very well. Then we need to write the program for this. So first of all, if you want to write a structural modeling, what we should know? We should know what is the basic component that is available there. Okay, so full adder is there, 1-bit full adder is there, right? How many such type of, is there any other element is there in this program, in this diagram? No, only the full adders are available. So therefore, one time full adder circuit we need to write. One time we need to write the full adder. Okay, so let us write the full adder module. Okay, the full adder is something like this. We can use the same names or different names also. Better use the different names. Okay, here we have an X input, for example. Okay, AB vardanandi. Okay, let us write AB here. A, B, and C. It will be sum. This produce C out. Okay, so how do we design this one? How many methods are there? As we have seen in the previously, this can be implemented either gate level, as you know very well. Gate level is possibility is there, data flow is there, possibility is there, and behavioral is possibility is there, right? And a structural modeling is also can be possible. Structural modeling, am I right? So inside of this one can possible to do any one of this stuff. Agreed? So anything can be possible here. Okay, clear to all of you? So therefore, depending upon your choice, you have to model the full adder somehow, and we have to call 4 times. As you wish, whatever the value that you can take it. Okay, so for the time being, just I'm interested to write the structural modeling itself. ఇది కూడా structural modeling లోనే రాశాను అనుకుంటున్నా. Okay, so I want to write. So it's possible to write anything, but say that for the for making some kind of difference, I'm saying that we are writing this one is also in the structural modeling. Okay, so what is the structural modeling that we have seen previously about it? Full adder, we have seen structural modeling in something like this. Okay, it consisting of two half adders are required. Okay, so I'm going to copy this one. Agreed? I'm going to copy this one. Okay, this is the one. This is the one way. Just a second. I think it is, yeah. This structure modeling very well we have already seen, and we have already done in previous classes. This is the structural modeling required. This is the program. Okay, I'm not going to do again this. So how the structural modeling is all about, all these things. Just I'm explaining that this full adder is implemented. So whatever the full adder that we have applied here. Okay, so this full adder is implemented by using half adders. Okay, so here I am following the structural modeling. The structural modeling is something like this. Here the constraint is that we have to use the half adders. Okay, so how the half adders look like, something like this: X and Y as S and C. I have implemented the half adder first of all. Okay, I need to test this half adder by using test bench. Okay, so whenever you're using some module, that we have to first of all describe, and we have to write the test bench. So I am assuming that I have tested this one, assuming that one I have tested this logic circuit, assumed. Okay, once it is thoroughly tested and verified everything is correct, then I have to call this one into the full adder. Okay, so here also I'm assuming that I have tested this is thoroughly assumed, tested. So by using the test bench. Okay. Okay, so once this is thoroughly verified, okay, by using the test bench, I'm calling this full adder into our main program. So better, I would like to say that instead of saying this is structural modeling, okay, so somehow I will write the simplest method, simplest way. What is the way that, what is the name? Let us give here. What is the name? Can suggest? Can anyone suggest the name? Ladder. FA. ST. Structural modeling. ST. A simple name that I'm giving. Okay, this need to be called 4 times. So better we have tried to A, B, C, S, and C, or C naught. Okay, then we have to change the name of this one also, C naught. Okay, so the C naught. Yeah, fine. Now, so we have to call 3 times this one, 4 times. So for top module, I'm writing. Okay, therefore let us write a module here. Top module. What is the top module here now? So this is the one. This is my top module. Now it is important for us to write the program for this. Okay, now this is the top module. So this top module consisting of what we can write, adder underscore 4-bit. That's what I have written. So this is the name that I have given. Here the variables are A, B, CAN, S comma C out, right? So input C1 input all are 4-bit size, 3 down to 0 of A comma B. Can we write the CAN here? Not possible, because CAN is actually a single bit size. Input 3 down to 0 of yes, sorry, I'm extremely sorry. This is not the one. It is CAN. Okay. Next we have an output. Output. What are the value? What is the size of this output? It is 3 down to 0 of yes. And next output is C out. Something like this. Okay. Since I'm a structure modeling, output need not be written in the data flow register data type. Okay. First I want to call first of all adder. So this one I want to call first of all. Okay. So if I want to call this one, I have already modified, I have already declared what it is. So something like this I have declared. Copy and paste here. I have copied and pasted here. So what is the point here is that the point here is that we have to give the name of this module. So this is for the hierarchical fashion. This is very important for us. So what is this name? FA0 we have given. So very important, FA0. So whenever we are synthesizing the circuit properly, then this kind of notation is very important. So name of the instant is important. Name of the module is important. Okay, so such type of blocks are required. How many number of times? Okay, better I'll do one thing. Okay, what is there inside of this one? As we all of you know, first inputs are there, next outputs are there, right? So I would like to write first of all FA0. For what is the input for A, B, C for FA0? What is the input for A, B, C? First input is okay. We can write it CN also, A0 also, B0 also. It doesn't matter. But good practice is that follow the A, B, C first of all. First we write A0, next B0, next CAN here, and then so that means that we observe that here is a A0 is here, B0 is here, C0 is here. What it will produce? Sum as an output, S of 0, next C of 0. Okay, C of 0. Okay, this is important for us. Okay, so therefore I'm removing all these things here now. So I want to place, this is the point. So the port mapping is assigned correctly now. So it's very, very important. Agreed? This is what we have seen already previously in all our classes also. We discussed these points more in classes also. Okay, so I don't want to take more time on this. So I want to copy this one. How many times such type of things are required? 4 times. Okay, so 4 times. Okay, let it be like that. Okay, but it's very important to note that we have to remove this one. What it is F1, F2, F3. Okay, but it's the same type. FAS underscore ST is the same type, but instances are different instances. 3 and 4 instances we have. It is very important to note that what is the inside of this modules also. Okay, these things are also important for us. Okay, let us write first of all what is the one. It is the 1, B1, 2, B2, 3, B3, right? What about C? The first C is nothing but C0. It is coming from C0. What about the next one? C1. What is the next one? C2. C up 2. Okay, so this is the one, this is the one. This is the 2. This is the 2. This is 3. So instead of C out, what I need to write? Here is C out I need to write. Okay, I hope I have done correctly. But thing is that C is not in inside C's are not mentioned. So I would like to write it as a wide data type, wire 2 down to 0 of 2 down to 0 na 0 1 2 0 1 2. Yes, it is a C. Okay, I hope I have done correctly. And finally, I need to write end module. Okay, this is how we need to write end module. Is it clear to all of you how I have written the structural modeling for header? Okay. Okay, fine. Here is the one question arises here. What is the test bench for it? Okay, let's write the test bench also. Let us write the test bench. Okay, so in the previous two cases, we assumed that the test bench is written and we have done very well. Now, in order to test this complete structure, this is also need to be tested. Okay, so test bench is required for us. Okay, let us write the test bench also for the more clarity. Okay, so this is what. Okay, so what things are not required here? So I'm keep on repeating the concepts repeatedly. So because you have to learn the things. I'm writing the test here. So inputs, all inputs are represented by a register data type. Register data type. All outputs are represented by wide data type. All these things are represented by wide data type. But internal structure is not at all required for us. So therefore, I want to remove this portion. So just delete this session, and we have to write the program for this. Okay, by the way, how many inputs that I need to declare? So it's very important to think about it. Is only we have to consider. So here, so I have to declare only these concepts only these parameters only I need to define. Okay, that's what the test bench. So if you want to, if I fully tested, if you want to fully test this 4-bit adder, how many combinations that it should apply? A is a 4, B is 4, C is 1. That means these are all 9 bits are there. Okay, 9 lines are there. That means 2 power 9 combinations I should apply. But actually, it's not correct in Verilog point of view. In Boolean algebra, this is okay. Boolean algebra point of view, it is okay. But in the Verilog point of view, it is 4 power 9 combinations I should apply in Verilog point of view. So it's not at all Verilog HDL. In Verilog HDL, these many, because it's a 4-valued logic, right? So it's very difficult to apply those many combinations. Okay. So instead, what we do, randomly we choose some combinations we will apply there. Okay. 4 or 5 combinations we will apply, very essential components only, and we need to test the circuit. Okay. All are on, all are off. Okay, 50% of the inputs are on, 50% of the inputs are off, something like that. Okay, but this randomness is also acceptable. Okay, so let us write initial here. Initial, let us begin here. So here A is here is 4-bit of here necessary. We need to write something like this. It's 0, and B is also 4-bit of all zeros, and Cn is equal to 1 bit of 0. Okay, this is the one case. Next, A is equal to 50% of the inputs I'm changing, 0 0 1 1, for example. B is equal to 4-bit of 1 1 0. So many combinations are there, it doesn't matter. Okay, C is equal to 1 bit of 1, for example. So it is after 10 nanoseconds. After another 10 nanoseconds, for example, A is equal to 4-bit of 0 1 0 1, for example. B is also a 4-bit of 1 0 1 0, something like this. And Cn is equal to 1 bit of 0, for example. Lastly, I want to conclude with this one. with A is equal to all 4 bits are 1 1 1 1. Okay, B is also all 4 bits of 1 1 1 1, and Cn is equal to 1 as well. Okay, so a set of bits I have given. Okay, finally I need to write end module. Okay, so this is what the test bench that we have written for this. Okay, I need to end the simulation, right? I want to simulate I want to stop the simulation for that one initial dollar, for example, 40 nanoseconds. Okay, I want to stop my simulation. Stop simulation. Stop or finish, both are there, but their uses are different. We can use this way. Okay, we can suspend the simulation at this time. Is it clear to all of you how I have written? Okay. So take this as a reference. Okay, I'm not saying that you just copy everything and do the things. Okay. So this is what the test bench and everything. This is the structural modeling. Okay. So I can write it structural modeling hub. I have I written there previously? Okay. Structural modeling hub, 4-bit full adder. Okay, this is what important. Okay. Usually the digital systems are a combination of different subcomponents. Okay, we have to take all the components. We do the structural modeling like this only. Okay, you have to practice in this way. HA is the subcomponent. HA is the subcomponent. Okay, so అంటే ఏమవుతుంది మనకి ఇక్కడ ఒక hierarchy is something like this. Hierarchy is, for example, we have a 4-bit adder. Okay, so 4-bit adder. So దాంట్లో ఏమన్నా మనకి 4 1-bit full adder ఉన్నాయి. Okay, so therefore 1-bit full adder ఉంది, 1-bit full adder ఉంది. సో దీని లోపల ఏముంది 2 half adders ఉన్నాయి. Half adder 0, half adder 1. Something like this. This is available for all this. This is called hierarchy. Oh shit. So this is called hierarchy. We can call it. Okay, so these are the main points that we have to remember. So these things is applicable for all these substations also. Please remember that. So this is called hierarchy model. Hierarchy model and the structural model, both are one and the same. Okay. So please take this code and try yourself that there should not be any kind of errors in it. Okay. Okay. By the way, another point also I would like to discuss here, and I want to stop after that. Okay. So this is the one way of writing the Verilog program. Okay. But for example, if I want to write a data flow modeling for this, there is a provision is there. I don't want to bother about, sir, you have written this much code, so I don't want to bother about inside of the circuit. I'm not at all interested on it. Okay. Is there any alternative way is there for this one? Okay, so it is a 4-bit size, as you mentioned. It is also 4-bit size. We have a CN signal. We have a S signal has a 4-bit size. Is there any other alternative without looking at the hardware inside of it? Okay, so whatever the inside of the hardware is not required for you means we have to go for the behavioral modeling. Okay, one such behavioral modeling is using the always block, or I can say that data flow modeling also. Okay, so what data flow modeling says that, okay, it says that we don't bother about what is the inside of the circuit, right? Okay, so this is what previously we discussed in the previous classes. Okay, instead of doing this one, we are making use of arithmetic operations. We are going to use some arithmetic operations. Verilog is providing you some kind of provision using the arithmetic operations. Okay, so let us consider some of the arithmetic operation. Plus is allowed, minus is allowed. Okay, some other things are also there, but when time comes, I'll discuss that point. Okay. Okay, so So I want to write this one equation. So for the arithmetic operations, I don't want to consider about internal structure, right? Agreed? We don't want to bother about the internal structure. But instead, we write arithmetic operators. What I can do is that, how do we define a sum signal here? We can write assignment statement, okay? So arithmetic operators are applicable to use only with assignment operators, okay? Assign S is equal to A plus B plus CAN, okay? So please remember that plus is meant for addition operation. Okay, so how this particular equation will be realized, that is used, it is implemented by synthesis tool. Okay, synthesis tool. Please remember that. So this is a comment, right? So better we write this comment in this way. So this equation is implemented by synthesis tool. So the synthesis tool will take the responsibility. Okay, according to your definitions, A is a 4-bit size, B is a 4-bit size, C is a 1-bit size. According to this one, it will choose the component from that library. It will generate that one. Okay, so when we add all these things, what will be the value of the sum here? It is a 4-bit size that is mentioned there. It is a 4-bit size. Okay, fine. It is a 4-bit implementation is available here. What about the cout? What about the cout? The cout is, we cannot write like this. How can I write like this? Assign cout is equal to, what is the value of this one? That means the result of this one we need to mention. What is the size of this result is very, very important. What is the size of this result? So since this tool will take 4 1-bit full adders, it will be added. It will produce as it is something like this. So it will produce something like this. So it will produce something like this. It will produce the 4 signals here and 5 signals. That means when it is adding 2 4-bit numbers and with the one additional CAN signal, it will generate, obviously it is generate the 5-bit value. It will generate obviously 5-bit value. Okay, so therefore that means, as you can see that S is actually a 4-bit size, that is the 4 bits are assigned to S. But what about the cout? How do we define the 5th bit of result? So that's very difficult to identify that. So that's why we have a provision, something like this. We can use the provision of concatenation operation. We can use the provision of concatenation. So what is the concatenation operation? Says that just we want to calculate the cout also, put comma there and use the curly brackets there. So whatever the result that is produced by this one is a 5-bit number, the result. So result is a 5-bit number. That result is assigned here. First 4 bits are assigned to this one. First 4 bits are assigned to this one. The 5th bit is assigned to this one. Okay, so that whatever the result is, that will be assigned to there. So this is the useful way of writing the program instead of the structural modeling there. Okay, whenever you are good at the programming, instead of taking, if the constraint is there, you can write it the structural modeling. If the constraint is not there, okay, then we have to go for the simplest method of data flow modeling. Agreed? So this is simply the data flow modeling of a 4-bit full adder with the help of Boolean equation, arithmetic operators. So please remember that the test bench is the same. Okay, so as we have seen previously also, the test bench is the same. Whatever the logic style that you use, it doesn't matter. We have to use the same test bench. Okay, does it require any kind of internal modules for this one? Any component is required? Not at all required. Okay, so please try, everyone from the class, please try to write the structural modeling. First of all, write the structural modeling, find the difficulty in it, and go for data flow modeling. Okay. So this is what you have to do. I will post this one to your WhatsApp group so that make use of this code and try to execute all the program and find the difficulties and solve those things. Once it is completed, I'll go for multiplexer. Okay. So, okay, I am going to make a snapshot of this, print this one, lab number 3. I will lab VLSI lab 2, lab 3. Okay. Desktop. Okay, fine. PDF. I will post this PDF to your CR. Okay, CR will please inform to send it to all the students.
Okay, sir.
I have to go to this one here. VLSI lab 3. Okay. Okay. Okay, all of you please solve these problems by using the Vivado tool. Okay. You have a plenty of time, is there? You can do it.